continuing with a roadmap now. We're starting over here and wandering all over the place. Yeah, it's roadmap and spider web together. So the second part of yours is going to be almost like this. The only thing I changed is these R groups. There's an R group on acetylene. I'll change it. Here's another R group on acetylene. There's acetylene in the middle. I'm going to change it. You're going to say he didn't, I mean, wow, he kept much the same. So what kind of reaction is this where acetylene becomes acetylide? And yes, you have to know that's acetylene for other parts of the exam. And a C-triple-C minus is acetylide, conjugate base. So what kind of reaction was that? I kind of just gave the answer, didn't I? Acid base. So acetylene has a pKa of what? 25. And NH2 minus is going to become, that didn't really cross out very well. NH3, right? What's the pKa of NH3? It's like an amine, right? 40. Oh, yeah, this reaction is going to work really well. It's got a negative pKeq, lots of products. So I've got my nucleophile. I need my electrophile. And what does the electrophile have to have on it? If you love electrons, you're missing electrons. Something in the nature of a positive charge. Now, don't put a cation there. You need a carbon that has an electronegative halogen on it. So in this case, here it is. Here's your group. The halogen has to be there, where the dot is. That's where I need the new bond. Bromine or chlorine, just use one of the two, okay? We're going to put the dot there just so you know that's where you need a halogen, where you're making that new bond. Let's have a halogen. Okay. And looks like we're making a bond on the other side. What were the two steps that made the bond on the first side? The bottom side right here. Step one, take the H off of acetylene to make a nucleophile. Yeah, nucleophile. Sorry. Pen's flying. Nucleophile is acetylide. The electrophile, carbon with a leaving group, halogen. Well, how do you make the C-triple-C into a minus? Do the same thing you just did. You want to use my base? Go ahead. 1. NH2 minus. Why not? You want to use H minus? It works too. So now you made a C-triple-C with a minus on top. Right there. It's ready to attack something. A carbon that has a halogen. What carbon has to have a halogen? This carbon has to have a halogen. You want to stick with Br? Why not? That's synthesis. You did 2 syntheses here. 2 new carbon-carbon bonds. Doesn't get more exciting than that. You see the name 2, 3, 4, 5, 6, 7. Phenyls on 1, methyls on 6. I need to make it into a trans-alkene. There's only one set of chemicals we learned that makes an alkyne that's internal. Yes, sodium, Na. And you need a source of hydrogens, NH3. So that's the one that makes the trans. We had 2 ways to make the cis. One of them's on the bottom right. H2 with Lindlar's catalyst right there. That is Lindlar's catalyst, in case you forgot. Lindlar's cat. So I'm going to draw my double bond. I'm going to put new H's on that are syn. And then I'm going to go to a CH2 with a phenyl. And I'm going to go to an isopentyl. 1, 2, 3, 4, 5. Done. So this one, cis. Hi. Oh. KH goes to R, C triple C minus, plus H2 if you're curious. Step 2, that's 1. R, C triple C. What's the pKa of D2O? Yeah, what's the number? 16? Yeah. And it puts a D there instead of a H, right? Just acid base, everybody. Step 1, take a proton off. Step 2, put a different proton on. It's a deuterium proton. Now, step 3 is the answer to this question. R, C, C, D. What happens during oxymercuration protonolysis? Because step 3 is just that. Oxymercuration and protonolysis slash. Protonolysis puts a H where the mercury was. There's an original H here. You get an enol here in red. It was an enol with an OH, but it underwent a tautomerization, oops, to become a ketone. That's a ketone. Okay. Yeah. D2O. You want even more information? D2O. Purple O. And... oh, we didn't want that. Sorry. I lost my mind. Water. AQ and purple. AQ. The black H was really purple. You want to review that mechanism, right? Purple H came from tautomerization. It did, I promise. So really the only answer there is this thing. Everything else was just logic going towards it. Okay, so that's a ketone on carbon 2, right? Ketone on carbon 2. Here's a ketone on carbon 2. No deuterium in the name. Yeah. Huh. Yeah. 1, 2, 3, 4, 5, 6. All the carbons are there. How do you put a carbonyl there and 2 new H's over here? That's water, by the way. Oxygen and 2 new H's. It's HgSO4, H2SO4, and water. Okay. Step 1 here. R. And you got new H here. but it's not an H. What's more electronegative? Tritium, which has the same electronegativity as hydrogen, or boron? Tritium. That's why it's on the more substituted carbon. Tritium. And B with Thia twice goes on the other carbon. That's step 1. What happens during step 2? You get rid of B, and here's an intermediate. I didn't put it in the box for a reason, because it's an intermediate called an enol, which is going to undergo tautomerization. R is CH2 once, twice, C with a V. And if you want, you got to show me the T here. There's a new H on there too, but I don't care, because there's an H on your picture right there. Good stuff. So step 2 starts off like this and then finishes like this. Tautomerization. There's a lot of extra stuff here. Really, I only need the final answers. I'm trying to help you study here. Okay?